Alright, now we'll continue our discussion in this compressive strength of flexural members without slender elements. Um, I'm always emphasizing um, this that this equation only applies to um, flexural buckling capacity um, of members without slender elements. Okay, so this is very important because if you have a slender elements um, and you want to calculate the flexural capacity, then you will have a different equation. You have to consult the codes and find the appropriate equations for for what you're looking for. And also, if you're calculating or if you want to find the capacity for torsional, or let's say flexural torsional buckling, then you have to find another equation. This equation only applies to this condition. Okay, this one, this Pn, this is our compressive strength, our nominal compressive strength, and this one should be, I guess, this one should be in kilonewton, kilonewton, not megapascals, because the strength in terms of these actual loadings, in terms of these compression loads, which is in kilonewton. This one is the critical buckling stress or load or stress, that's in megapascal, and this one is the gross area. Now the question is, where do you find this gross area? That's from the table. This one, the critical buckling stress, this depends. Okay, so how do you find this? We have these conditions. We have to check if the slenderness ratio, take note, this one is slenderness ratio. The other one that the other one denoted as lambda, that's just what we call the slenderness, but it's actually the limiting width to thickness ratio. This one is the slenderness ratio. Okay, if the KL over R is less than or equal to 4.71 square root of E um, Fy. Okay, and take note that's different from the limiting values of the um, slenderness or this limiting value. That's different. This one is 0.56, this is 1.49. Um, but this one is 4.71 square root of E all over Fy. And if the slenderness ratio is less than this value, then our equation would be Fe R FCR is equal to 0.658 raised to Fy all over Fe times Fy. Okay, so that's our equation for this FCR if the slenderness is less than this. If KL over R is greater than 4.71 square root of E Fy, then our critical stress FCR is equal to 0.877 Fe. Okay, this condition can also be in terms, instead of the slenderness, it can also be in terms of this. The critical, I think the Fe is the critical buckling stress. Okay, if Fe is greater than 0.44 Fy, then this is the equation. But if Fe is less than 0.44 Fy, then the equation is this one, FCR equal to 0.877 Fe. Okay, so now what is this Fe? This Fe is just simply the pi squared E KL over R squared. Okay, so that's our or critical buckling stress. This one is a FCR. That's just the critical. Okay, so I guess a lot of terms are mixing up already, but um, that's the notation. So let's just say this is the stress. But when we say Fe, that's the critical buckling stress from the Euler equation. Now let's try to convert this in a graph. We have this graph, and recall that this is, let's say, the load, and then this is the slenderness ratio, and this is KL over R, and this one is in, I think that's in or could be let's say in terms of the stress FCR. Recall that we have this limiting value for yielding, and we have another value for the buckling, and the actual column curve, or the AISC curve, is something like this. And we have this, if we apply this limiting value, this KL over R, this 4.71 square root of E over Fy. Now if we have this, or if we are beyond this value, then our equation is 0.877 F sub E. And here, if you are below this, or less than or equal to 4.71, then your equation would be 0.658 Fy or over Fe times Fy. Alright, now let's discuss the slenderness, and then after that we'll discuss the procedure for the analysis. For the slenderness, the code says that for members designed at the basis of compression, the slenderness ratio is preferably should not exceed. So the slenderness ratio is I think that's the KL over R and not the lambda. The scale over R should not, or not this K. I think just the L over R. The slenderness L over R should be less than, or should not exceed. So meaning it is less than or equal to 200. Okay, and slenderness is also one of the limit states. As usual, and I remember that's also included in our tension members, the limit states for tension members. So that should include also as well. So meaning we have 3, 4, 5. So this one is slenderness. This one is local buckling. And then this one is the flexural buckling, and torsional buckling, and the last one, that's the flexural torsional buckling. Okay, so this one is something like a check to determine the equations that we are going to use if if it has a slender, if the section it has a slender elements or not. Okay, so now let's talk about the procedure for analysis. Okay, so again, when we say analysis, we have the cross section, we have the geometry, we have the details, and we just have to find the capacity or the load, how much load can it um, carry. So the first one, so the first step is to obtain the necessary data. For example, you're given this section and it has some details. For example, 250 by um, 250 by 167. Okay, this one is the nominal depth, and this one is the mass per. I think that's the mass per length. So once you're given with this section, then you have to go to the table to obtain the necessary data. So for example, we have to find the gross area, and we also have to find the depth. For example, the Rx, Ry, the this thickness of the flange, thickness of the web, or you can refer to the compact section criteria. Okay, so if it's available, then we can just use it. So for example, the compact section, we have BF over 2 DF. So you don't need to compute that manually. So there's data for that already. And for example, for the web, we have HC times the thickness of the web. Okay, so you need to have this data. Okay, once you have that, then you have to determine the lambda sub r, that's the limiting width to thickness ratio, and compare to the slenderness, to the section slenderness. Okay, so is this is this BF over 2TF is less than or equal to 0.56 square root of E over Fy? Okay. Or if you check the web element, is the H over TW is less than or equal to 1.49. The next step now is to determine the governing slenderness ratio. Okay, governing slenderness ratio. Okay, so this slenderness is KL over, slenderness ratio is the KL over R, and we have to check if it's the KL, it's along the X or along the Y. So which one governs? And once you have this, you have to compare to the limiting value of 4.71 square root of E all over Fy. Okay, and after that, we have to solve for FCR, the critical stress. So this one will dictate if KL over R, if the governing slenderness ratio is less than or equal to the 4.71 square root of E all over Fy, then our FCR, the critical stress equation, is 0.658 Fy all over Fe times the Fy. But if KL over R is greater than 4.71 square root of E over Fy, then our FCR is 0.877 Fe. Now, once you have the FCR, then you can now solve for the design capacity, and that's VPN is equal to the reduction factor for compression members for compression and times FCR times the area, and this reduction factor is 0.9. Okay, so just a brief review on this procedure for analysis. Uh, we, we first have to find the necessary data. For example, the area, the radius of gyration along x, along y. We need this value to solve for the slenderness ratio. And there's also a value already for the compact section, for the slenderness. So, take note, the slenderness is different from these. This slenderness is different from the KL over R. This is the slenderness ratio. This one is just referred to as slenderness, but actually this refers to the width, a more precise definition for this is width to thickness ratio. Okay, so KL over R, and now this is the slenderness ratio. Now this slenderness, we have to check that this slenderness on our webs or flanges on our elements. We have to check that to the limiting value of, for example, this one, the flange. I think this is the unstiffened elements. Then this is the limiting value. Then you have to just substitute the E and the Fy, and you have to check the slenderness or this width to thickness ratio on the web and compare that to the limiting value. Now, if our section is not slender, then we can proceed to our calculation. If not, if we find out that we have a slender elements, then we cannot proceed any longer because we didn't tackle those topics. Okay, so the next step is to solve for the governing slenderness ratio, KL over R. Then after that, you have this FCR. You can solve for the critical stress, and once you have it all together, then you can find the design capacity. Okay, so I guess this is a lengthy discussion so far that I've made, but the discussions earlier that we had in the previous two videos, they're necessary in building up our knowledge and skills on this equations or in this analysis. Okay, so a lot of terminologies that we have encountered, and some of them they're just a review, or probably we have forgotten already the concept or the principles behind those principles. But once we understood that, and we understand the where would we go, or where do we look it up in the codes, the tables, the equations, the conditions, we just have to understand that, because once you understood that, then you can you're good to go. Alright, so enough of this discussion. In the next video, we will do a sample problem for these compression members. Alright, see you in the next video.